We will now solve some examples of second-order differential equations with discontinuous forcing terms. Our first example is y double prime plus y equals 0 when t is between 0 and 2, but then it turns on to the forcing term, which is a constant 1 when t is greater than or equal to 2. So we need to rewrite the right-hand side of this differential equation using Heaviside functions. So here we have y double prime plus y is equal to, and by the definition, this is just h of t minus 2, a function that starts at 0 and then turns on to 1 when t is greater than or equal to 2. Now, just like we did before, we need to take the Laplace transform of both sides of this differential equation. So we're going to take the Laplace transform of y double prime plus the Laplace transform of y. And that's going to be equal to the Laplace transform of the Heaviside function of t minus 2. So the Laplace transform of y double prime is going to be s squared times capital Y for the Laplace transform of y minus sy of 0 minus y prime of 0, and then plus the Laplace transform of y, which is capital Y, and then that's going to equal the Laplace transform of the Heaviside function of t minus 2. So that is e to the minus 2s over s. The e to the minus 2s comes from the Heaviside function of t minus 2. And then 1 over s, of course, is the Laplace transform of 1. Now I'm going to substitute in my initial conditions. Y of 0 in this case is going to be 1, and y prime of 0 is 2. So what we have here is that we have s squared plus 1 times capital Y is going to equal, I'm going to move some of these terms to the right-hand side, so I'll have an s plus 2 plus e to the minus 2s over s. I'm going to solve for y, so y in this case is going to be s plus 2 over s squared plus 1 plus e to the minus 2s times 1 over s times s squared plus 1. So what we need to do here is we can rewrite this as s over s squared plus 1 plus 2 times 1 over s squared plus 1 plus e to the minus 2s times, and then what I need to do here is I need to look at the 1 over s times s squared plus 1, and I need to split it up using partial fractions. So I'm going to do a little bit of work off to the side. I'm going to say that 1 over s times s squared plus 1 is going to equal a over s plus b s plus c over s squared plus 1. That tells me that a times s squared plus a, so I've multiplied top and bottom of 1 over s by s squared plus 1. Okay, plus, and now I'm going to multiply the other top and bottom by s, so I'm going to get b s squared plus cs. That whole thing has to equal 1. And that's 1, if you think about it, plus 0s plus 0s squared. So that tells me that the coefficients of s squared, a plus b, must equal 0, which of course tells me that b is minus a. And then The next term, the S terms, tell me that C has to be 0. And then finally, we have that A, which is the only constant term, has to be 1. So we get that A in this case is going to equal 1. And so that tells me that B in this case is going to be minus 1. So if A is 1, we get a 1 over S. And then if B is minus 1, we get minus S over S squared plus 1. So this is Y. And now I need to take the inverse Laplace transform to find little y of t. S over S squared plus 1, that is the Laplace transform, of course, of cosine of t. Plus 2 times 1 over S squared plus 1 is the Laplace transform of sine of t. And the e to the minus 2s is going to give me an h of t minus 2. And then we have that 1 over s is actually the Laplace transform of 1. And then again, we have that s over s squared plus 1 is actually the Laplace transform of cosine of t. But everywhere we see a t, we're going to replace that with a t minus 2 because we have the e to the minus 2s in front. So the basic fact that I'm using here is that the Laplace transform of the Heaviside function of t minus 2 times cosine of t minus 2, the Laplace transform of that is equal to e to the minus 2s times the Laplace transform just of cosine of t, s over s squared plus 1. And so what we had to do is we had to do that in reverse and say that the inverse Laplace transform of e to the minus 2s times s over s squared plus 1 is actually h of t minus 2 times cosine of t minus 2. So that is our solution. It's cosine t plus 2 sine t plus the Heaviside function at t minus 2 times 1 minus cosine of t minus 2. And what you should see here is that this solution really has two pieces. The first piece is the cosine of t plus 2 sine of t. And that comes from this equation, y double prime plus y equals 0 with these initial conditions. And then once we add on the forcing term of 1 when t is greater than 2, that is what's actually adding this piece to the solution. So we have a solution in yellow that's essentially a response to the initial condition for that differential equation, y double prime plus y equals 0. That's the homogeneous linear differential equation. And then what I have in orange is a response to the change in that forcing term. We changed it from 0 to 1. So if we were to plot this in Desmos, what you have is I've defined the Heaviside function first. H of t is 0 when t is less than 0, and it's 1 when t is greater than or equal to 0. And so then I plotted h of x minus 2, and I had to use x here because Desmos likes to use the variable x. So in red, you see h of x minus 2. And then in blue, what you see is the cosine of x plus 2 times sine of x. And that's what it is initially. And so you can see up until t equals 2, that's going to be the curve cosine of x plus 2 times sine of x. But you notice that there's a shift in the solution that actually starts when t equals 2. Okay, because initially you could see that the amplitude was going up to just a little bit above 2, But now, after t equals 2, it's kind of shifting my solution up. And so now we have kind of a different looking solution after t equals 2, and that's in response to the forcing term.